Let's describe the bonding in an ethyne, also known as acetylene, molecule C2H2. We're also going to count up the number of sigma and pi bonds. Now, ethyne is a systematic name for the simplest alkyne, which means there's a triple bond between two of the carbons. Let's draw the lowest structure here. Carbon has 4 valence electrons. There's 2 of them. Add that to hydrogen's valence electrons, which is, since there's 2 hydrogens, is 2. Gives you 10 valence electrons. To draw the lowest structure, you need to put carbon in the center. Hydrogen is never the central atom. Let's put the 2 hydrogens around it, form a bonding pair, connect all those atoms. So there's a bonding pair there, bonding pair there, and bonding pair there. Those are your shared electrons and covalent bonds. So we've used 6 of the 10 electrons to bond these, and now we have 4 valence electrons left. You can distribute them equally around the carbons, and you'll see that the central carbons do not have an octet. So you'll have to make a double bond and then eventually a triple bond. And so there is your low structure for your ethyne molecule. Let me clean this up a little bit. So to quickly answer this question on your test in terms of the number of sigma bonds, you just count up all the single bonds. They're always your sigma bonds. So there's one there, there's one there, and the first bond of every multiple bond is also a sigma bond. So there are 3 sigma bonds in ethyne. Now, pi bonds, by the way, sigma bonds are your head-on overlapping of orbitals. They're going to be more stable than your pi bonds, so they're always going to be the first one to form. Now, your pi bonds are your second and third bonds in your multiple bonds. So there are 2 pi bonds in this molecule. All right, so let's talk about the bonding in this molecule. I'm going to use an energy diagram to illustrate this. So for that central carbon, if we draw the valence electrons, it has 4 valence electrons, 2 in the 2s orbital, and 2 more in the 2p orbitals. Following Hund's rule like that. And then let's just draw so those are the 6 electrons you would use to configure, and this is energy going up like that. Now, in order to have bond angles around this central carbon that are 180 degrees, you can't do that with these sets of orbitals. You can't have one spherical shape, and you can't have 3 dumbbell shaped. You can't use any combination of these orbitals to form equivalent bonds that are 180 degrees apart from each other, right? Because these are all 90 degrees from each other, and this is just a ball looking thing. So there's no way you can take 3 of those shapes and have equal orbitals of 180 degrees. So that's the point of hybridization. When we need 2 equivalent bonds, we need to mix one of the s's. So we need to mix carbon's valence s orbital with one of carbon's valence p orbital, right? Forget the core electrons. They don't do bonds. All right, so when you mix carbon's valence s and one of the p's, you get a hybrid orbital. Since you're mixing 2 orbitals, you get 2 hybrid orbitals, right? And this is known as your sp hybrid orbitals. Now these ones here are unhybridized. They're just your normal, I don't want to use too many colors. These are just your normal unhybridized p orbitals. All right, now let's redistribute those 4 electrons, those 4 valence electrons. All right, so that's, and this sp, these two sp hybrid orbitals have 50% s character and 50% p character because you're using one of the s's and one of the p's, so you get 50% character each. Come on. All right, so I'm gonna clean this up a little bit. Actually, I'm gonna redraw this. I just redrew that a little cleaner right there. So these 4 electrons represent the valence electrons for that carbon, and I'm just going to copy that the same for the other carbon next to it. Yeah, that's good. All right, so I hope you can see that. All right, those are the orbitals for that carbon, and those are the orbitals for that carbon. All right, so now we're going to show you how these form sigma bonds. Now hydrogen, I'm going to just keep in black here. So just to recap, an s orbital looks like this. It's a spherical shape. A p orbital looks like this. You can say it's a dumbbell shape. And then if you mix them, you get an sp hybrid orbital. It might look like that. All right, so that's kind of what these things look like. All right, so I'm going to just focus on this section of your screen, that carbon on the left. That carbon on the left is right here, and it has there's an sp orbital. I can do that a little better. There's that sp orbital, and then the other one is looking the other way. So now you can see why we needed those, because now we can make 2 equivalent orbitals that are 180 degrees apart. All right, so I'm going to do hydrogen in this little gray color. Hydrogen only has an s orbital, so one of its valence electrons in there. Actually, hydrogen only has 1 electron, period. Right, and then here's that electron there. Okay, so there's that sigma bond right there. Okay, so now I'm going to go draw this carbon over here. Now that carbon also has 2 sp hybrid orbitals. So I'm going to draw them now. One is overlapping with the other sp from the other carbon, and the other one's facing the other way. All right, so now that electron is in there, shared with that. There. Okay, so there and there. That's that sigma bond right there. All right, and now let's go to the right and draw one more hydrogen over here. There's the s orbital for hydrogen. Hydrogen only has 1 valence electron, and then here's that valence electron there. Okay, so that is that sigma bond there. So hopefully you can see right now the 3 sigma bonds that I've drawn. Now let's draw the 2 pi bonds. Those are going to come from the side-to-side overlap of the p orbitals. Now you might be wondering, why can't the p orbitals just face this way? Well, they can't face that way because these guys are there. Remember, electrons repel each other. They don't want to be in this area because those sigma bonds are there. So the p bonds, if you recall, one of them's already in here because it's hybridized and it's mixed in there with that other s. But these 2, all right, one of them is going to be in the x direction. So this is your px, this is your py. And this is your px, this is your p on the y orientation. The pz's are part of this head-to-head sigma bond. All right, so I'm going to pick 2 shades of green here. Is what I'll try. All right, so the px's I'll do in this green. There's your px. There's your p orbital. Okay, your p orbital in your x direction, and they're overlapping in this region. Okay, they don't look like they're overlapping, but I don't want to clutter up the screen. They are. All right, so you might say this electron and that electron are in this region here. Right? That region is just 1 pi bond. That's 1 pi bond, not 2. Right? Because it's an overlapping of the P from this carbon and the P from that carbon. All right, so that's that pi bond. Now there's another pi bond perpendicular to that one, and they're all perpendicular to each other and perpendicular to the sigma bond. All right, so this is the py. Right, and so they're also overlapping side to side. Right, that guy you'll find in there somewhere, and that guy maybe you'll find in there somewhere. So those are in green right here. That's your pi bond there, and that's your pi bond there from the side to side. They can't overlap head to head because the sigma bond is there. All right, to recap the video, which I had to redo because I left out that very important part, is why do this at all in the first place? And it's because when you have a central atom, let's call it X, and you need 2 equivalent orbitals, and they're 180 degrees apart. You need a linear structure, in other words. You can't get that from an S and a combination of 3 P's. So you've got to mix one of the S and one of the P's, and therefore you need SP hybridization. All right, so just to recap the key points to quickly answer the questions on your test. All single bonds are sigma bonds. And any first bond in a multiple bond is also a sigma bond. Your double and triple bonds are your pi bonds. When you need 180 degree bond angles, then around the central atom, you need to hybridize one S and one of the P's to get sp hybrid orbitals. And because you'll get 2 of them. You get 2 of these guys.